Well, hello everybody. We've had a fantastic 2 days learning about magnitude of sea level rise and the regional influences. But what I'd like to focus on is some of the impacts and costs, particularly focusing in Europe because we had an EU project there. So I'd like to share some of those results from that and also some other work that we've been doing in Southampton. Now, Andy, I'm not sure whether to thank you or not for the talk beforehand, either setting me up or actually taking some of my slides, because the first one is all about Hurricane Sandy, and this isn't the only one that's identical. So a year ago, we were sort of thinking about Hurricane Sandy and the effects that was having along the American coast. And of course, there were very large impacts to the coastal zone. We had many houses flooded. We had effect on tourism, effect on shipping in the area, along the infrastructure as well. So it affected a large amount of people and also had a large amount of costs. And we could expect events to happen more frequently as sea levels rise. Now, it's not just the developed countries that get affected, it's also the developing countries too, as you can see on some of the slides there. So we really need to think about the broad-scale things, broad-scale impacts that are happening in our environment and how they all interact with each other. So in this talk, I'm first of all going to look at relative sea level rise and other drivers of change. Secondly, we'll be looking at projections of sea level rise and some modelling that we've been undertaking in Southampton. Before looking at some of the costs and adaptation as well, so a little bit similar to Andy, but hopefully some new information there too. So first of all, looking at relative sea level rise. So here we go, another talk looking at some tide gauge records here. I've selected these as a good selection around the world, going from Amsterdam, looking at some very long tide gauge records, to Bangkok. Now, when we're looking at tide gauge records, again, it's very important to try and understand the causes of change. So in Bangkok here, we've got this very high rate of rise, up to about 13 millimetres per year, and we know that's due to water abstraction. So we need to try and understand why these changes have happened in order to do something about it. So moving on, we can also think about projections of sea level rise. Jonathan talked yesterday about looking at high-level projections, how IPCC are not so certain they're going to happen because they're not yet confident yet with the data behind it. But we can look at some of the projections here, potentially 2.4 metres per century. AR5 came in a lot lower, about 82 centimetres of rise by the end of the century, which is slightly less than AR4 for reasons, slightly more than AR4 for reasons that were discussed yesterday. Another problem on our coast, it's not just all about sea level rise. As Andy said, it's also about population change as well. So it's really important how we engineer our coastline to actually think how we're going to adapt about sea level rise. This is some UN data looking at population change. You can see here it goes from 1950 right up to 2010 of actual population change. The red line there you can see is Asia, and the green line at the bottom is Africa. Now, out of the world's population of 7 billion people, of course, we would expect the Asian population to be greatest. But in the future, it could go a number of ways. So these are different population projections. We could have a high level with Asia there increasing still, or alternatively, population could decrease. Africa also continues to increase throughout the 21st century. And all these people have to live somewhere, they have to be somewhere. And where they live and how we engineer our cities or our urban environments can actually be very important when we're actually considering the potential impacts of coastal change. To focus that a little bit more on the coast, we've got a map here looking at coastal population in the low elevation coastal zone. So that's land below 10 metres that's still connected to the sea. You can see that the darker colours are those that are most sparsely populated, with the red colours, which you can't actually see on the map because it's very, very small states, are much more densely populated areas. We can also start to add in cities. So we know here from the low elevation coastal zone that areas, say in Asia, mega deltas in particular, so around sort of Bangladesh, the Ganges, Brahmaputra, and also the Nile Delta has got very high populations. But if we try and add in cities now, you can see how that just tries to focus that a little bit more. The solid blue, sorry, the darker blue colours represent those cities that are already greater than 8 million people and that will potentially grow maybe up to 40 million people. Yes, the lighter blue actually looks at those that are 25, in 2025 could extend up to, again, that 40 million. We've got some there that are emerging in Asia. You can see some new megacities emerging, as well as one in Africa as well. So we know that the coast and the population that's going to live there is going to change, and that's really going to affect our impacts. So in this talk I'm focusing on Europe, but why Europe? The map previously, if I just flick back to that, you can see that we've got quite a few people living in low elevation coastal zones, rather much more high population density in some countries. And that's really important, therefore, to study and see how these people could be affected. We have important cities that are very important for trade as well, and so that could have knock-on effects to those who live not just on the coast but further inland as we transport goods and services around. We need to try and understand the costs and impacts from a strategic planning perspective. So, as Andy was saying, we need to try and look at these long timescales to actually see, well, what could we do today to actually reduce impacts in the future? And having good projections of sea level rise and understanding of how sea levels are changing are part of that. So, all in all, we need to try and understand how we can better protect the coast or adapt our coast to try and reduce impacts, not just in the short, but also the long term as well. So, looking at projections from the study and looking at some of the modelling that we did. So we looked at potential sea level rise. We looked at a number of scenarios. I've just pulled out two here. So we've got an A1B scenario, which was a 3.5 degree rise at the end of the century compared with a baseline of 1980 to 1999. And that projected a 37 centimetres worth of rise. We also had this green line, which is our E1 mitigation scenario. That was about a 1.5 degree rise by the end of the century with 27 centimetres worth of sea level rise. And you can see that these two scenarios are fairly similar until you get to about 2050 where they start to diverge, and that's because of the commitment we have to sea level rise from warming in past times. So by the end of the century we've got, well, in the 2080s we've got about 10 centimetres of difference between those scenarios, but what's 10 centimetres? Does it really matter? And that's one of the questions that we have to try and answer within our project. I've also added in this scenario here of no sea level rise, and that just acts as our baseline to actually make us better understand whether it's social economic change or relative land change in terms of what's contributing towards our impacts and costs. Now, there is, of course, uncertainty around those, but I've left those out just to keep things simple in this presentation. But we do have that uncertainty range if anybody would like to sort of talk about that at the end or come and ask questions. Those scenarios that came from their HEBGEM2 model, we've got the spatial pattern here. It's quite difficult to see Europe, unfortunately, because it's down the dividing line. But you can actually see this is our impacts avoidance. That's the A1B scenario minus the E1 scenario. So we also took that into account during our calculations. In order to look at projections around Europe, we used a model called DIVA, which is short for Dynamic Interactive Vulnerability Assessment, which is a bit of a mouthful. DIVA breaks the world's coastline down into about 12,000 segments. Each segment is an average of about 70 kilometres long. If we focus in on the European Union, which was just what we looked at for our project, the coastline segment there had an average length of about 45 kilometres, and it happens to be this red one up in Scotland. Some of those segments are actually a lot shorter, a couple of hundred metres, so it's quite a variety of lengths. Each segment was associated with different pieces of information, so we had things like GDP, population density, information about coastal slope, information about subsidence, and all that information could be used to try and understand the coastal processes. Now, when we're looking at very large-scale segments such as this, we kind of do often get asked the question, well, is this information actually right? Is this too broad? Can you really represent coastal changes at a 70-kilometre coastal segment? Well, there are some issues there of actually trying to be consistent, but when you're looking at this, because this is a global scale model, it gives us a good estimate of what's going on and gives us a flavour of where we can actually look at more detailed studies in the future. So we know we're kind of heading in the right direction, but of course it's not actually suitable for those local scale studies. So I'm not an oceanographer, but in very broad terms, how we're looking at coastal change is that we're looking at changes in the return period. So here we've got the return period curve, and so for example, if our sea levels increased, our return level there increases, which means that our return period there could reduce, say, from a 1 in 100-year event to a 1 in 10-year event in the future. So we look at those changes to see the amount of land loss and the people that will be affected and the costs associated with that. So actually trying to build up what's happening on our module methodology, we've got social economic scenarios here, so that takes into account to GDP and population growth. We also look at, say, sea level rise and also temperature change as well. And we also look at adaptation. Now, of course, there's many ways that you can try and adapt on the coast. You can build walls, you can build wetlands, you can actually nourish beaches. So in our model, we've just looked at building dikes and nourishing beaches, just because this is two simple ways that you can model on a global scale, except there are other ways, but for simplicity purposes and modelling, that's the easiest way that we can go for the time being. So in terms of what we looked at in terms of adaptation, we looked at with adaptation, so upgrading defences as sea levels rise and population expands, or we looked at no upgrade to adaptation. So we modelled adaptation in 1995, which is our base level, and we just assume that stayed constant. It's not a reality, of course, because we know that defences do get upgraded around Europe, but it gives us a baseline, sort of the worst case scenario. So we initialised our data set, and then we looked at all these different impact assessments and much more as well, looking at storm surges, backwater effect, salinisation around rivers and land. We looked at wetland change as well. And once we had all that information, we also then could put a cost on it. And the two that I'm going to talk about today are damage costs and also the adaptation costs as well. So the parameters that we investigated, these damage costs, we've got values here in 2005 euros. We look at sea floods, river floods, land loss, salinisation, and people that have to migrate because they are flooded year upon year upon year. We also had a price on adaptation as well. So in adaptation, we just took into account of sea dikes, river dikes, and also the beach nourishment as well. So with that, we ended up with these three scenarios, our A1B, E1, and no climate change scenario, each partnered with a with upgrade to adaptation or no upgrade to adaptation. That's sort of the worst case scenario. So I'll just try and show some of those results here for our European coastline. So we had 22 countries to look at. In EU projects, we find a benefit of working on the coast is that you get less countries to study than other people, but we still got quite a lot of work to do. So it doesn't count Norway, these results, or some of these Mediterranean nations here as well. So these are some of our initial outputs. So we've got here in 30-year means to the end of the century, and we go up here to about 30 billion euros worth of cost per year. Now, I did a presentation very similar to this back in March, but I was very busy in March, so I prepared it in February, and I thought, well, what nation is very similar to outputs to sort of this level of cost per year to give a good comparison? And unfortunately, I chose Cyprus. Cyprus has a GDP per year of about 20 billion euros. But the day before I gave the presentation, it was all up in the news about having all the financial disaster in Cyprus, so it wasn't the most appropriate one to do. But that kind of gives you an idea about what costs are. Another controversial scheme in this country is High Speed 2. It's a new railway network the government are proposing. And the costs of that are about 50 billion euros worth of infrastructure. So in terms of what we're looking at in this graph, we're looking at like a major infrastructure investment year upon year upon year towards the end of the century, and of course beyond, sea levels continue to rise. Now, the solid lines here represent the A1B with no upgrade to adaptation, whilst the dotted lines represent with upgrade. So the red ones here and the green ones and the yellow ones in the 2000s, so in our present time frame, are actually fairly similar, coming in about 3 billion euros per year. But we can see that increases as time goes on due to sea level rise and also population change as well. Population change and social economics actually becomes very important. If you look at the 2050s with the no upgrade to adaptation, so the solid lines, you can see that the E1 scenario there has actually more damage costs than the A1B scenario. So that doesn't really make much sense because sea level rise is less. But because the social economics are different, it means it has a different output. So we need to be aware of that in the long-term future. It's not just about sea level rise, it's also about other forms of social economics and population growth and GDP as well. By the time we get to the 2080s, we're finding damage costs could be about 25 billion worth of euros per year. If we mitigate, so that's that 10 centimetres difference in sea level rise, our cost could go down to about 17 billion euros per year. The important thing is also to say it's not just about sea level rise again. No sea level rise scenario here, we still expect to get damage, and that's because of just relative land levels change and social economic change. But even if we do mitigate and we do adapt, which is this dotted green line, we're still going to expect some damage, of only not a small amount, so about 3 billion worth of euros per year. And that kind of gives us some reality check that we still have to continue to protect the coast in some way, just to be and make sure we're doing that in a good fashion. So Based on the discussions yesterday, we also talked about an upper end of sea level rise, and Jonathan was saying about how it's very difficult to sort of pinpoint that. So we also ran 1 metre's worth of sea level rise. So I added in a slide last night to try and explain that. So this is on going up to 160 billion euros worth of cost per year. So you can see with a 1 metre sea level rise, we suddenly get this very big jump from going from about 30 billion euros per year up to nearly 160. So the key message is that if sea levels do rise beyond the 37 centimetres unmeasured for the A1B, costs could potentially come a lot higher. There is a step change, and we may not be able to afford all around Europe to protect to that level. Indeed, we may not want to, for reasons that Andy said, making sure that adaptation is appropriate. If I just flick back to the previous slide now. Here we're sort of suggesting that adaptation is quite a good thing. It can reduce our damage costs, but is it actually worth it? If we actually apply a cost-benefit analysis, is it actually worth doing? In a very crude way, you can actually show this. So again, keeping it 30 billion on that y-axis here, and just adding in the adaptation costs. And you can see the costs here are actually much, much lower. So it gives us an idea that adaptation is actually a good thing to do. It can reduce your damage costs, and that can benefit not just the coastal zone, but the wider community too, and it's affordable to do. To take a reality check on that now, we can add in what the EU, well, presently, this was 10 years ago, actually spends on coastal adaptation. In the erosion documents, it records at about 3.2 billion euros there in 2001. So although we've got about a third less than that, we're at the right order of magnitude. And there's good reasons for why there are differences. There's different types of adaptation. We could be from wetlands. We could have multifunctional defences, whether you sort of build shops and houses on top of your defences. Think about the Dutch examples. So there's many different things and many different protection standards as well, which actually can explain those differences. So we know that we're in the right direction at least. So damage costs. I've given you the European example, but how are they spread throughout European nations? Again, we've got green colours, the least amount of damage. The red colours here and orangey colours that you can see in northwest Europe are ones that have experienced the highest damage. So really we're looking at the UK, France, Germany and the Netherlands potentially having the highest damage costs if you don't protect and upgrade defences. Netherlands is perhaps a little bit less than that. We're using a global model with some generic rules here, but we know their defence standards are much, much higher. So it could mean that those damage costs are potentially a lot less. So knowing that Northwest Europe has potentially high damage costs, what does that mean? Are people doing anything about this? So I found then a paper, it was led by Richard Toll. It was published in 2008. The data is probably a little bit older than that. It actually looked at awareness of sea level rise and climate change around Europe. And what Richard and colleagues did was to map this, or categorise this, so in terms of very low awareness, so the ones in red, to very high awareness, those in green, so the colours are the opposite way around here. And what they found, if we compare those two figures, is that the countries that potentially have the highest amount of damage are those that are most aware about sea level rise and climate change, and most proactively doing something about it. Now that data is a little bit old, but in the review of the literature, we've actually found fairly similar results, that the relationship between one European country to another is actually fairly similar. But over the last 10 years, awareness has generally been raised all throughout Europe, which is a good thing. So people are actually thinking about sea level rise a lot more. So in terms of adaptation, what does this mean? I suggested a few slides ago that adaptation is a good thing because it does reduce damage costs. So we have three main options. We can have planned retreat, so we can actually move away from the coastal zone, so we could be part of managed realignment of actually letting the coast go. So we can choose to do that, or it may happen accidentally in some cases. We can accommodate sea level rise, so we could raise buildings. I had a trip to Germany in the summer, and although they've got a big dike, this is on the Baltic Sea, though they have a very big dike in front of the houses, they've now got planning regulations that any new builds there actually have to be raised, so if the area flooded, the house would effectively become an island. So that's already been put in place, not just in Germany, but other countries as well, about actually thinking about the long-term implications for the houses that are going to be there for potentially quite a long time. We'd also go back to hard and soft protection, how we traditionally protect the coast. So even though we have those different types of adaptation, we also have to think about how appropriate they are. As Andy said, so you get times where there are issues with the coast where you get increased erosion if you protect in one area and the knock-on effect on the others. So we really have to think about how we're best going to protect the coast, not just now, but also in the long term, and how that actually fits in with lots of different sorts of environments. Two examples of this are in Rotterdam and Hafen City in Hamburg. So in Rotterdam here, they're really looking at the way ahead, looking at climate proofing, making their city much more sustainable and energy efficient, of actually trying to think about where the problems are, and they're leading away on that. In Hamburg, they've redesigned part of their city. They've raised buildings, they've actually by several metres, and it gives quite a clear message that they're open for business and provides that confidence for the business as a whole in that area, that they're open for business come what may. So those are examples. Not everybody's like that, but it actually makes you think about that we can actually adapt in the long term. So some conclusions then. First of all, as we know, mitigation will not stop the rate of sea level rise. We're going to continue to have sea level rise. That rate may decrease, but it does mean that we're going to have the problem in the long term. So we need to think about long-term solutions and raise awareness over that time period as well. And part of that's future monitoring. We need to try and understand what's happening and why and where and all those knock-on effects. And some of those presentations we've had earlier today and yesterday have actually really shown some good questions we need to think about. So secondly, social economic change is also very important. How we manage our cities and plan is going to be increasingly important in the future, particularly in maybe Asian cities as well that are expecting large population growth. Adaptation is going to be essential. We need to think about how the best way is to do it though, and it seems a worthwhile investment, but we need to think about flexible ways of doing it if we're not really certain about how much our sea levels are going to rise. Overall, though, we need to think about broader coastal zone management. It's not just about sea level rise. We need to think about what people would like in their coast in the future. So we need to think other drivers of change. So I think as a closing statement, I mean, as stakeholders and users of the coast, how would you like your coast to be managed in perhaps the next 10, 20, or even 100 years' time? Thank you.